All right, welcome everybody to your last chemistry class, well, actually, yeah, I guess this would probably be your last chemistry class ever at the college. So welcome. This won't take us too long, I hope. We're going to finish chapter 3 and, depending on the time, I'll show you I guess the important parts of chapter 4. Chapter 4 is on waste management. Chapter 3, of course, is or was on atmospheric chemistry. So what I'm going to do today is go through a couple of gases, specifically picked gases that are covered in this course that are atmospheric hazards. So I'm going to start right away with section 3.2.1, carbon monoxide. Carbon monoxide, an interesting gas, very, very toxic to humans. It comes from car exhaust and other things, but it's a really interesting and quite toxic gas. So the way that this works today, we will look at 3 gases. We're going to look at carbon monoxide, sulfur dioxide, and nitrous oxides. And each gas, we're going to look at the same thing. We're going to look at how it affects a human body. We're going to look at acceptable limits, sources in the environment, and then ways to minimize it. So these 4 outcomes that you see, they're good to know for your final exam, and 2, they're the same for the 3 gases. So we're going to look at, again, how does it affect the body? What are the acceptable limits? Where does it come from? And how can we minimize it? All right, and then we get into chapter 4. So carbon monoxide, they call it the silent killer. It's got a name because it is such a dangerous and toxic gas. And one of the reasons why it's so dangerous is because it's colorless and odorless and tasteless. Now you think of a lot of gases, think of the atmosphere itself. A lot of these gases, they don't have a taste or an odor or a color. So things like oxygen and nitrogen, we don't taste them, we don't smell them, we don't see them. They're just there. That's fine because those gases are safe oxygen we need to live. Carbon monoxide is toxic and dangerous for humans. So if you were in a situation, a car, a factory, a plant, where the carbon monoxide was high, above a dangerous level, without an electronic sensor, you wouldn't know. Okay, that again, like if I ask you why is it so dangerous, it's because it's colorless, odorless, and tasteless. So the gas, if it filled a room you were working in, a slow leak was happening, you wouldn't really know. So a lot of industrial plants and a lot of areas, well, even I guess most homes these days would have a carbon monoxide detector. Your smoke detector in your apartment or villa or wherever you live, your smoke detector should have a sensor for carbon monoxide. If not, you can buy specifically designed carbon monoxide sensors because, again, as a human, you can't detect it, but the sensor can. So carbon monoxide in the atmosphere is spatially variable and short-lived. So spatially variable, meaning it's in different amounts in different places. It's short-lived, and it does have a role in the formation of ground-level ozone. So again, the big takeaway here is that it's colorless, odorless, and tasteless, and that it is different depending on where you are on Earth. In a heavily polluted city, for example, there would be more carbon monoxide than, say, in the Swiss Alps. So, excuse me, carbon monoxide is toxic to humans, hemoglobic animals, when encountered in concentrations above 35 ppm. And typically with these gases, the acceptable levels are after a certain time period. So depending on the government website you go on, or the scientific journal or article, the acceptable levels are usually after like 1 minute, 10 minute, 1 hour. And the acceptable limit here is 35 parts per million, and after about 1 hour exposure. It is produced in normal human or animal metabolism, and it is thought to have some functions in your body. But in high amounts, again, above 35 parts per million, if you were in a room with it for over an hour, it is toxic to hemoglobic animals, including us. Humans. Carbon monoxide is present in small amounts in the atmosphere because of volcanic activity, but also from man-made and natural, anthropogenic, I guess I should say, fires and natural fires. So some forest fires, bush fires, they can be caused by nature, natural, meaning humans didn't have a part in it. Lightning strikes a very dry forest and it ignites and there's a forest fire. So that can produce carbon monoxide. Humans have been known for centuries to be burning things in large scale. You can use fire to burn off crops or sugarcane. These contribute to carbon monoxide, but chiefly in the environment, you get a lot of it from volcanic activity. The burning of fossil fuels. So this is, the big one when they talk about climate change or, the greenhouse gases. Burning of fossil fuels is a big one. It comes from the exhaust in your cars or vehicles. So when you burn gasoline or fossil fuels to power your car, it produces from the hydrocarbon combustion, it produces carbon monoxide. And again, this is a greenhouse gas. All right. So not good and very dangerous, right? So if you're in I could go tell a few stories here, but I'll tell a quick one. So my neighbor in Canada, my parents' house, we have neighbors on each side, and one of my neighbors is a small engine repair mechanic. So he's a mechanic that works on, well, anything smaller than a car, we'll say. And he is also an avid snowmobilist. So if I'm not sure how familiar you guys are with this, but he likes to ride like skidoos or snowmobiles. I don't know if you're familiar. Anyways, little snow machines that go on top of the snow. Long story short, he was in his shed. So like behind his house, he has a small workshop, we'll call it. And he was in there working on his skidoo or his snow machine, and he had it running for a little while. He was doing some tests. He had it running, and the carbon monoxide, the exhaust from this snowmobile, built up in the shed. Anyways, my other neighbor, was walking by that night, luckily, and had decided to go visit my friend. He saw the light on in the workshop and he decided to, pop in, say hello. Anyways, when he got in there, he found my neighbor on the ground, passed out. So again, carbon monoxide. Now, I know when you have a car or a snowmobile or whatever, when you burn the fuel, you can smell the exhaust. But whatever reason, he had the window open, he had the door open, but he didn't think it was bad. And he was in there working, and it got so much that he, passed out. So yeah, he had to go to the hospital. He's fine. His son actually had to go to the hospital too. His son was in there for a short period of time, not as long as his father. But yeah, they had to go to the hospital and into like a hypobaric chamber. I don't know the biology of it. I'm a chemistry instructor, but he was fine. But yeah, my neighbor saved his life, and it was again because of the burning of these fossil fuels made carbon monoxide, and he had carbon monoxide poisoning. So very dangerous, kind of scary. So in an industrial size or an industrial, a scale is what I'm trying to say. When you're working in a plant that maybe has diesel engines running or, burning fossil fuels, carbon monoxide sensors are really important. So the easiest way for humans to reduce, I mean, we're not going to go stop volcanoes. So the most effective way for humans to reduce carbon dioxide is to reduce fossil fuel consumption. So moving away from burning hydrocarbons and into different energy sources, even moving away from hydrocarbons in general. They're used in everything, right? We'll never get away from them. Well, not anytime soon. They're used in pharmaceuticals and plastics and, of course, energy sources. But if we could reduce carbon dioxide or fossil fuel consumptions, we should be able to reduce carbon dioxide and monoxide emissions. Sorry, I kind of skipped into carbon dioxide here. Very similar, both are products from incomplete and complete hydrocarbon combustion. Not quite awake here yet. So many strategies for reducing carbon monoxide, carbon dioxide emissions are basically energy reducing tactics. So they can apply to homes, businesses, industry, transportation. Again, could be an electric car, LED light bulbs, anything that can reduce cutting energy. All right. So other examples to reduce carbon dioxide, like I said, improve energy efficiency, reduce the use, switch to a renewable resource, or carbon capture and sequestration. I'm only circling that one, not because it's the most important, but because you might not be too familiar with this compared to the other three. It just means, when you say burn hydrocarbon, you can capture the exhaust, capture the waste, the product of the chemical reaction, and convert it into something else, or capture it instead of letting it go into the environment. Sequestration means the same as like capture, so catching or collecting the carbon as it gets produced. All right, I'm going to do two more gases. It's going to be the same as that, and then I'm going to move into chapter 4 and we're finished. Okay, so the next one, sulfur dioxide, SO2. I don't know if you guys remember that from Chemistry 1200, you're naming, right? So di means two, so sulfur, SO2, sulfur dioxide. We will again state how it affects the human body, what are the limits, and how do we reduce it. So sulfur dioxide, chemical formula SO2, like I mentioned. At standard atmospheric pressure, it's so, 1 atmosphere, normal Earth pressures or sea level pressures, it's a toxic gas. And this gas is different than carbon monoxide. It does have a pungent, irritating, rotten smell. Some people say it smells like eggs, or, I mean, you even hear people say that something smells like sulfur. The smell of sulfur is typically rotting eggs, really pungent. It's hard to explain over Zoom, but you've all probably smelled it. If you've ever walked around an active volcano, you might have smelled it. Even if, like in your kitchen, if you've overcooked an egg, like a hard-boiled egg, for example, if it's been overcooked, it gets this green ring around the yolk. And when you open the egg, you can kind of smell it. I mean, that's like a little hint of what it smells like. It's really stinky. And this gas is released naturally by volcanic activity. So a lot of these gases are released naturally as well by volcanoes. The EPA, again, I'm using Americans as the example here, has set the air quality standard. This is where I got the 35 ppm, by the way. Well, they've set the standard here for sulfur dioxide at 75 parts per billion over 1 hour. So think about carbon monoxide. It was only 35 parts per million. Sulfur dioxide, you need a lot less of this to be toxic, 75 parts per billion. excuse me, over 1 hour. Now, again, the thing about this gas is, we would hope, or typically, if you were in an environment where this gas was being produced, you would smell it. It's unlike carbon monoxide or even carbon dioxide, this gas has a smell. And sorry, speaking of carbon, there's a typo here. I really should fix this. I'll fix it after class. I probably said that last semester too. I mean sulfur dioxide here. So reduction opportunities for this, there's not as much literature I could find available for this as I could for carbon, but the easiest ways I could find were to clean up smokestacks and exhaust pipes. So again, you can tell this comes from fossil fuels. You'll see kind of like a trend here where all three of these gases are produced from burning fossil fuels. So reduction opportunities here, just clean up the smokestacks and exhaust pipes where the sulfur dioxide residue can collect. And of course, I mean, honestly, guys, wink, wink, between me and you, if I ask you on your final exam, wink, wink, to maybe talk about how to reduce any of these gases, this is kind of the blanket answer. If I ask you how to reduce carbon, sulfur, or nitrous oxides, you can just say this, right? Use alternative energy sources. Again, a lot of these gases are byproducts of the burning of hydrocarbons. And again, you might be wondering, how does something like nitrous oxide or nitrogen dioxide or sulfur dioxide come from burning hydrocarbons? Just remember, fossil fuels are hydrocarbon based, but that's not the only product that's in there, and that's not the only thing we get from their combustion and use. So it's not just carbon and hydrogen that are, products. I was going to say adverse products or bad products from the burning of fossil fuels. But this is a really good answer. If I ask you, how do we reduce this gas? You could always just say, well, we could reduce our dependency on fossil fuels. All right, you notice that was really short. There's not a whole lot of information in that section. And I'm going to do this last section, and then that's it. This is a little longer, and I'll talk quickly about section 3.3. I don't think I'm going to cover everything here, and we'll get into chapter 4, and that's it. So section 3.23, we're going to look at the last gas. We will talk about the effect of nitrous oxide. So that includes nitrogen monoxide and nitrogen dioxide on the body. Talk about limits, talk about the sources, how do we reduce emissions? You can imagine here what we can do. I'll put a little winky face, right? How do we reduce emissions? Lower fossil fuel consumption. So nitric oxide or nitrogen monoxide, excuse me, and nitrogen dioxide, the sum of them, they usually just call nitrous oxides, or NOx is an abbreviation for that. There are other oxides, of course. There's nitrous acid, nitric acid. There's a lot in the nitrogen oxide family, we'll call it. But looking at the EPA's website, it covers the entire family, and NO2, nitrogen dioxide, being the most important, or it says here, the component of greatest interest and the indicator for the larger group. So I will talk about nitrogen monoxide and nitrogen dioxide, but looking at EPA, which is the government standard similar to other countries, NO2 is the component we're concerned about the most. So current scientific evidence, and when I say current, I did the research for this maybe 2 winters ago, so 2018 or early 2019. I don't think much has changed since then. Short-term nitrogen dioxide exposures, 30 minutes to 24 hours, can have adverse respiratory effects. So airway inflammation in healthy people, and very important, increased respiratory symptoms in people with asthma. So nitrogen dioxide, a healthy person can inflame their airways. Somebody like, for example, with respiratory illness like asthma, it can really increase their symptoms. So obviously not good to breathe in. Like if you think about all three gases together, carbon monoxide still stands out to me as one of the scarier ones, in the sense that you can't smell it, you can't see it, and instead of respiratory symptoms, like if you were breathing in carbon monoxide, you wouldn't even necessarily cough or your lungs wouldn't burn. What I've read is you get sleepy and you fall asleep. It's pretty, I don't know how to put this. It sounds really weird to say it, but it's calming almost. It will put you to sleep, because it's blocking your oxygen levels to your brain, so you kind of get put to sleep. And sulfur dioxide has a really pungent, stinky odor. I mean, you'd know if you were smelling it. Nitrogen dioxide, it's starting out symptomatic, meaning, your airways might get inflamed. It would increase your respiratory symptoms. So carbon monoxide kind of stands out to me as really scary, because if you were in a situation like my neighbor where you had high levels, he didn't even know. And, he was up working on his engine, and then he was asleep or knocked out on the ground. So, yeah, it's kind of interesting to think about. So nitrous oxides, they can react with ammonia, moisture like water, and other compounds to form small particles. These particles can penetrate into the sensitive parts of your lungs, and this is where the respiratory illnesses or respiratory issues happen. It can cause or worsen respiratory disease, such as emphysema and bronchitis. It can then it can also aggravate other existing diseases, heart disease. So breathing nitrous oxides, it can lead to a hospital admission or even premature death. So again, carbon monoxide can kill you on the spot. The health effects of nitrous oxide seem to be more long-term and more of a condition that you might be hospitalized for. Very dangerous, very bad gas to be breathing in, but it's the effects don't seem to be as immediate as, say, carbon monoxide. Ozone, you heard of the ozone layer. If you can't remember what ozone is from chemistry 1200, I don't know if you even learned about it. When I say that, I mean you should have. It's one of the gases that have a special, they call them trivial IUPAC names. So ozone is O3. And it's formed when nitrous oxides and volatile organic compounds in the presence of heat and sunlight get together, we form ozone. Ozone is also a toxic gas. It's obviously in the atmosphere. We have the ozone layer that has been protecting us for years against UV rays. But in high levels, ozone can be a toxic gas. And some of you probably have, I would say maybe most of you have smelled ozone before. If you have done a lot of photocopying in your life, and I don't know if this might be a teacher thing, but if you know that, like I can picture right now, even though I'm home and I haven't seen one in a couple months, which I think is a good thing, a photocopier has a smell. And that smell I can almost picture or smell right now. The smell of a photocopier is the same smell as ozone. So ozone is a byproduct of nitrous oxides and other compounds reacting with heat and sunlight. Children, elderly people, people with lung diseases like asthma, people who work or exercise outside are at risk for adverse effects from ozone. So again, this is long-term effects, not like carbon monoxide, and it's really impacting lung function and respiratory symptoms. So one of the standout things, I will ask you about these gases on the final exam. Again, think about these outcomes when you're thinking about your final. What do they do to humans? What are acceptable levels? Where do they come from? How do we reduce it? Well, just, when you're thinking about all these gases, carbon monoxide, can lead to death. Sulfur dioxide, nitrous oxide, nitrogen dioxide, whatever, seem to aggravate longer term symptoms, respiratory symptoms. Okay. So for the level, again, I'm using the EPA here, same website as before. The EPA, the last time I saw that they updated this was in 2010, so 10 years ago. I don't think these levels change too much. The EPA said the safe standard is 100 parts per billion over 1 hour. I say safe standard, I mean the limit. So 100 parts per billion over 1 hour would be the limit that, anything above that is hazardous to human health. Oh, guys, I would say this to my normal class. Not saying you guys aren't normal, but if this was a normal semester and we were doing the exam in the gymnasium, you don't have to memorize these numbers. I will not ask you about these numbers. If and when you work with environmental health and safety, you'll have a book or the internet that has all this information. But, just know the differences between the gases and maybe where they come from and how we can reduce the emissions. You don't need to worry about the numbers. So we have 35 parts per million. So I think it was 75 parts per billion and now 100. So where do they come from? Well, when fuel is burned at high temperatures, fossil fuels, they come from mostly motor vehicle exhaust and stationary sources. So not motor vehicles, but things using hydrocarbons, electric utilities, industrial boilers, anything that's using a hydrocarbon as its fuel. Nitrous oxides or nitrogen dioxide is in high levels, is a suffocating brownish gas. It's a strong oxidizing agent. So it can form corrosive nitric acid as well as different toxic organic nitrates. So, really, really bad chemical all around, and it can form other types of toxic chemicals as well. All right, so that's it. Oh, and again, I didn't really mention this here. How do we reduce it? Well, if these gases are coming from burning fuel, if we can reduce, the hydrocarbon combustion or reduce burning this fuel, we can reduce the sources of nitrogen dioxide, nitrogen monoxide. This is a source we did earlier. I think it was chapter 2 of acid rain as well. Okay, so just bad for the environment in general. And any of these gases, guys, carbon monoxide, sulfur dioxide, nitrous oxide, whatever gas we're talking about, they can be reduced by lowering the burning of hydrocarbons or fossil fuels. All right, cool. So guys, I think that's pretty much it for chapter 3. I'm just going to skip through this. Guys, you don't really need to worry about section 3.3 for your final, but I will skip through to a couple of important slides and then we'll get into chapter 4. So section 3.3, the reason I say you don't have to know for your final is any of these numbers, I'm not going to ask you about these numbers. Again, if you went to work in the United States or Canada or Japan or here in the Middle East, the guidelines would be different based on the country that you're in. The air quality standards vary from country to country, and this is something you would have with you in a book or you would use the internet. What I'm saying is this is not something you need to memorize. So I'm not going to really ask you about this on the final. And then there's methods for sampling that this would have been the last lab, but because we're doing the labs online, because of the situation that we're in the world, we only did 5 labs. And this lab, I wouldn't be able to do at home anyways. I'd have to go to the college to get the equipment for this. So this would have been the last lab, but we didn't get to do it. So these are, this slide here, again, guys, you don't have to study this last section, 3.3, don't worry about it. You don't have to look at it for your final, but these are just different levels. You can see some of the numbers are drastically different, right? So it depends on where you go. There's not much to say about these numbers, but this is from, I think, 2018, these numbers. And this is the EPA, which is USA, versus Qatar's standards or guidelines. So you can see not every country has the same amounts or even system. The USA, what I found was 3 hours, here is 24 hours, things like that. So if you don't work in the Middle East, maybe you go work somewhere else in the world, they'll have their own set of guidelines. Like now, this might not be true in 2020, but when I was researching this in 2018, I didn't find anything for ozone. So, some of these things might be updated every year as well. All right, now the last thing I'll say for this chapter, again, you don't have to study this at all. This would have been the lab, but we didn't get a chance to do it. Sampling gases, excuse me, is a little different than sampling water. Sampling water, I remember I showed you how to collect a water sample in a bottle. Sampling air, how do you collect air in a bottle? Typically, we use a vacuum, which this is what the lab would have been. We have these small pumps that create a vacuum and draw the air into a chamber, and the chamber holds a special absorbing solution. And again, this is all the lab, and we monitor the rate of flow. We use a flow meter. If you guys were at the college right now, we would be out in the parking lot doing this near running cars, but this is such a weird time that we didn't get a chance to do it. A lot of industries or factories, even the college itself, will have air pollution sensors on property. And these sensors detect and monitor air pollution in the surrounding area at all times. An example of this, probably above your head right now, is a smoke detector. Okay, that's an example of an air pollution sensor. It would sense things like carbon monoxide levels. They're in homes, they're in plants. That's kind of it. And I'm going to leave it there. You guys, you don't need to read or study section 3.3. So with that, it's 10:15. I'm going to get into the last chapter, chapter 4. And I'll only do a couple things from this. There's a few outcomes that I really want to show you. And then that's it. We're done this whole course. A little tiny bit faster than maybe I wanted. Sorry, I'm just trying to share my screen here. Little maybe faster than I wanted. It would have been nice to have that class on Thursday. Or maybe to not have missed those classes during Eid, then I could have maybe taken a bit more time, but we are pretty much getting everything done. So this is, it's good. You can see how this course, I love it so much for intercession because it's pretty straightforward. There's no rush or anything like that. So guys, I'm going to just introduce and do a couple little bits from this chapter and we're done. I just looked at the attendance. I only have 5 of you here today, or 4 of you. Nobody's here today. You guys must have some work to do this week, I think. For the people who are here or anybody listening on YouTube, try to stick around for the end. I won't be much longer, maybe 15 minutes or so, but try to stick around for the end just so I can give you a couple little updates for the final. I will have a tutorial or an optional session on Wednesday in your lab slot. I'll be on Zoom for any questions. I'm around tomorrow as well, Thursday as well, but I'll just give you guys a little heads up about the final before you leave at the end of this class. So if any of you guys have to go who are here right now, Just check the end of the YouTube video when it's uploaded. All right. So Unit 4, waste and waste management. I actually didn't cut anything out of this unit yet. The notes, there's only 30 slides. These are the notes that I give in a regular semester. Whether or not I'll get to all 30 today, I doubt it, but I will show you all of the kind of the highlights or the the most important parts from this unit. This is it. So our last chapter, waste and waste management. So the first section here, we'll look at hazardous waste, and you can kind of see a few of the outlines or outcomes I've highlighted, and a few are in gray down there. These notes, by the way, guys, are online. If I would highly recommend opening or printing or just having your phone, your tablet, something with these notes open when you're doing your final. So we'll look at the definition of waste. How is waste harmful to the environment? Look at common categories of waste, and then the outlines that we're not going to do because, of course, we're not in the college right now. It says prepare and inventory chemical waste at the college. Identify proper disposal procedures for each type of waste identified. We're not at the college. We're done with the labs. But if this was a normal semester, I might get you guys to do this, to prepare and inventory some chemical waste for me. We do it as instructors all the time, but obviously we're not at the college right now. We can't do this. So waste, I think, guys, this is my favorite definition in the whole course. Waste is unwanted or unusable materials. I love it. It's so simple. It's so common sense, right? Think about what waste is in your home. Everything you throw out, paper towel or an eggshell, these are unwanted or unusable materials. Now, unfortunately, a lot of the things we do throw out, I just mentioned eggshells, they're not necessarily unusable. You could use eggshells for composting, but in general, waste around the world, like a plastic bottle, an aluminum can, if you don't recycle them and throw them away, I mean, it shouldn't be waste, but it's waste. So it's any substance which is discarded after its primary use. It's worthless, defective, and of no use. Again, guys, though, the examples I gave aren't really the best, because if you think about it, most things are not worthless or have no use. They can be recycled. So waste here is kind of a loose term. I mean, if you were asked on the final exam on how to reduce waste, reducing waste, the easiest way would be to, lower the amount of things you're using, or you could reuse the amount of things you're using, or you could recycle the things that you're using. So the definition of waste here, a little loose here, because, there's an old saying, one man's trash is another man's treasure. So what's unwanted or unusable in one place to one person might not be unwanted or unusable to another. So, waste, kind of an interesting, but still my favorite definition. So people earn their living by collecting and sorting garbage and selling them for recycling. So again, an important thing to know here, what one industry or one person or one company, what they call waste, might not actually be useless and could be sold or recycled. This picture, back home, I know we call it the dump, D-U-M-P, and you can go to the dump, but I don't think they let you do this at the dump. But I know people do this at the dump, and they go and look for things, treasure hunting, we'll call it. But anyways, the picture is to illustrate that not everything, is what's unusable to one person might be usable by somebody else. So the term is subjective. Okay, we say subjective. Waste to one person, not necessarily waste to another, and it's objectively inaccurate. So, putting scrap, like the example I give here is putting scrap metals into a landfill, that's not really correctly classifying them as waste, because you can recycle scrap metals. Again, I mentioned like throwing an aluminum can away. or throwing a water bottle away or throwing an eggshell away, that's it's inaccurate to call that waste because they could be recycled, or the eggshell, for example, used in composting. So examples of waste would be municipal solid waste, household trash, refuse, so things that you throw away that can't be reused. Hazardous waste, wastewater, sewage, obviously I won't go into detail here, but bodily human wastes, surface runoff, radioactive waste. There's a lot of types of different wastes out there. And again, if you can't reuse it, that it would be considered waste. As technology advances and we learn more about different chemical processes, the recycling process is getting better. So, hopefully in the future, we'll see less and less waste because we can find a way to reuse this. Or, there are chip bags now, potato chip, or if you're British, they call them crisps. There's chip bags now that are biodegradable. So that's not technically waste because when you throw it away like waste, but it would dissolve or degrade into the environment very safely and naturally. I guess that would still be waste, but it's not hazardous, we'll say. So inappropriately or poorly managed waste can attract rodents and insects. That's hard to say. And these insects and rodents can harbor parasites, so bring with them disease like the plague. Rats famously carried one of the most dangerous diseases to ever spread around Earth. Poorly managed waste can be very, very hazardous to the environment and humans' health. Sometimes, I'm sorry, I'm just kind of skipping to the bottom here. Some countries, some different places, they burn their waste. So, they fill a landfill up with waste and then burn it. This can cause various other respiratory diseases or lung cancers or different types of cancers. Poor waste management is a career, someone's job, and poorly managed waste can really have adverse effects on not only the environment, but humans or our well-being. Sorry, I just wanted to, okay. I kind of know what I want to do here, or how far I want to get today, because we're running a little low on time. So toxic waste materials can contaminate water, soil, air, cause problems for humans, other species, ecosystems, kind of the whole web of things. Waste treatment and disposal procedures, like greenhouse gas emissions, methane, these are contributing to climate change. So again, you might not think of greenhouse gases as waste, but they're a byproduct of burning fossil fuels, for example, and they have no other purpose, most cases, just to pollute the environment. So there's different types of waste and their effect on the environment. Now, this is kind of leads into what we would do in the lab if we were getting to the lab. Industrial waste. So again, like you guys as environmental health and safety people, you're probably not going to be, thinking about things like somebody throwing away an aluminum can. You might look at industrial levels of waste. And I just mentioned a minute ago, properly managed waste is really important. And it's, someone's job, usually some manager, is to look and monitor and take care of the waste from an environment, waste management expert, we'll call them. These people typically in an industrial setting classify chemical wastes, label them for proper disposal. You don't just throw all of the waste in one place. So there are 4 characteristics chemical wastes have to be considered hazardous. And this kind of leads into the last part of the course where I'll talk about labeling. So this is you can see the source on the bottom. This is just a rough guideline of chemical waste disposal that different plants or companies might take. So you can see there's like 4 categories here, 4 colors. So we have innocuous aqueous waste. These are included in this liquid waste. These can be washed down with excess water. You have acids and bases, harmless inorganic salts, alcohol-containing salts, hypochlorites, that's like bleach, fine silica, and alumina. These are waste that you could wash down with excess water. Then you have these other three wastes. You have organic waste. They can be chlorinated or not chlorinated. Oh, I never noticed this, guys. After all these years, there's a typo there. When we dispose of things in the lab, for example, at the college, any chlorinated hydrocarbons are thrown out in separate waste than non-chlorinated. So if you were in my, say, hydrocarbon chemistry course and we were doing labs, we do use some of these organic solvents. They're specially discarded in special waste bins. There's the red list here. These are compounds with transition metals. You can see mostly here, we have mostly metals. Fluorides and nitrates are in there, cyanides. There's different types of metals in this list. And then in the last list, solid waste. So this could be lightly contaminated waste like lab or hospital gloves, empty vials, syringes, broken glassware, things like that. So this is just an example, not the example of a waste disposal guideline. Every company, every industry, our lab, for example, at the college, we have guidelines, we follow government regulations, we dispose of things based on a particular guideline, and this is just one of those guidelines, okay? All right, so I'm not gonna spend, okay. Sorry, I just want to skip ahead for 1 second. Guys, this is kind of another section that I won't ask you about on your final, section 4.2. This is local regulations. These are things, depending on where you went to work, what country you worked in, each government, each municipality, each country even has their own waste regulations. So you don't need to know this section, but if you are curious, you can go. Now, this, I think, has slightly changed in recent years. If you are curious, I think you can find most of this through the Ministry of Interior. And I know that, but when I was making these notes and I was updating them a few months ago, the website wasn't as clear as this website, which in 2008 was still available. And these services still exist. They're just a little different to find them. But you can see some environmental services there that the government here has. So not really much to know for this section 4.2. You don't have to memorize it for the final or anything, but depending on where you go, which country you work in, they'll have their own environmental services, radiation and chemical protection. This would include disposal and storage, something like chemical shipment, you'd get information there, construction specifications, this would fit in with occupational health and safety and environmental health and safety. And you probably have looked at this in other courses as well, I would hope or think. And again, if you're looking for this now in 2020, I think you'll find most of this information with the Ministry of Interior in a subsection with the environment. All right, the Americans, they would use the EPA. Qatar here is through the Ministry of Interior. And these are laws, again, you don't have to know that. Okay, so guys, you can kind of, if you're curious, you can read and look through 4.2, but I'm going to finish off today's class. There's 8 or 9 slides left with this section. A few more minutes and we're done. The last section, guys, this section, there will be some questions on this on your final. Okay, so I am going to kind of highlight and explain some of these things for you. This would be our last lab of the year, and this is a really kind of interesting section. It's about waste storage and processing, and it won't take us too long. So 2 outcomes to cover today, and then that's it. We're going to look at proper measures for labeling and storing lab waste, responsibility of lab technicians to properly label, store, and process this waste. And I mean, I know you guys aren't in a lab technician program, but an environmental health and safety situation where and it doesn't need to be a chemistry lab like at the college, but anywhere that's using some of these chemicals, this kind of fits to all industry. They should be properly labeled, stored, and processed. We don't in the lab just throw everything down the sink or into the garbage. They are proper. If we can't throw them in the sink, dump them down into the water, we label, store them, and then eventually send them away for processing. Okay, so just very quick, couple slides and you're done. Lab waste. Packaging, labeling, and storing, wink wink, are 3 requirements for disposing chemical waste. Before you can dispose it, and again, at the college, we send this away for disposal typically. So we get special companies in the country to dispose of this safely for us. But before we do that, we can't just throw it in a bottle in the fridge or on the shelf and not have it properly labeled, safely packaged, and stored somewhere before we do the disposal. Now, this is a picture I found. This is actually maybe not the best picture. The labels here are not very good, and I'm going to explain good labeling. And this is not our lab. This picture I just took, I think, from the Wikipedia here. But there are better ways to label the waste. I mean, this is okay, but there are better ways. So guys, wink, 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 you should know about the packaging, labeling, and storage of waste. And I'm going to do all these 3 very quickly, and that's it. For packaging, chemical liquid waste containers should only be filled 75%. The reason is it should allow for any expansion of that liquid, whether it's freezing or whether it's the gas is expanding. It can reduce potential spills as well when you're moving overfilled containers. This is really, really important, guys. Make sure when you're packaging liquid wastes, you only fill them about 3/4 full. And again, this gives room for moving it around, for if it's, say, frozen, because liquids usually expand. I know water does when it's frozen, or even for vapors to expand if it gets too warm. The other thing about packaging is, okay, so you only fill it about 75% full, you leave it room. The other thing, and this is a big thing as well, the material of the container has to be compatible with the waste. Some acids react with different substances. Some different materials might oxidize or might react with other different substances. So when you're storing waste, you want to think about plastic or glass or something else, different polymers, metals, whatever you're working with. The container material must be compatible with what the material is, sorry. This information you can usually find in the material safety data sheet. Okay, so you don't have to know this or memorize this for any chemicals, but you can find what type of material this would be reactive with in the safety sheet, the MSDS, which you guys, I hope you've heard about before. In addition to the general packing requirements, incompatible materials aren't used. So waste must be stored in containers compatible with the chemicals stored. Solvent safety cans can be used to collect large volumes of flammable organic waste. And we do not mix anything else into these cans. So that's another really important thing. You can mix some types of waste. Like we can mix different organic solvents into 2 categories, chlorinated or not chlorinated. This is just an example, but you typically don't mix different types of waste. So I wouldn't mix something flammable with something that's highly oxidizable, like sodium metal or magnesium metal or something like that. I wouldn't mix a strong acid with a strong base. I mean, that's just a very simple example. The last thing, and then, or last two things, I guess, and we're done. Once you've picked suitable packaging for your container, so it's not overfilled, it's in a material that's safe, glass or plastic or a metal can, you have to label that. The label should include the group name from the chemical waste category, a list of all of the contents, because again, you know, if I have a label, a bottle that says organic waste, well, then I need to label it what's in there, you know, what type of organic chemicals are in there. And then all chemicals or anything contaminated should be listed if they pose a significant hazard. All waste, again, must be properly packaged and labeled. Like in the lab, we get in huge trouble. I think I've only seen it once, and nobody knows who did it. This is 5 or 6 years ago, but there was a bottle of waste in the back of the fume hood. Nobody knew what it was. It could have just been salt. It could have just been something safe, but it wasn't labeled. So we had to spend, you know, countless amounts of money to get it properly disposed of. Some company had to come in and figure out what it was and dispose of it. And again, it could have just been table sauce. Like, we didn't know. So every, you know, type of waste that you have, if you're not pouring it down the sink or throwing it in the garbage, it needs to be labeled. And this is an example of a good label. So again, this picture back here, not the best labels, but this could be a good label. It would include the chemical name, the manufacturer. The manufacturer can help. Sorry, I don't mean to put a star by that, but the reason, if you're wondering why the manufacturer, this can help. If you don't have the MSDS available, sometimes the manufacturer's website or, you know, a manual from the manufacturer might have information about how to store and dispose of this. So you have the chemical name, the manufacturer, the MSDS number. Here you have categories of the waste, so you could check them off. This is, by the way, just a sample. This is not the label, it is just a label. So this label, you could have check off health issues, flammability issues, reactivity issues, and then maybe it would be something different, a special hazard. Down here, you can write any personal protection required. So you could fill in any special requirements here, like, you know, where not to store it or how to carry it or shouldn't be moved or things like that. So this is just an example of a label. And the last thing, 3 slides and we're done finally, the storage. So we did packaging, labeling, and then storing. When you store chemical wastes, first things first, the containers must be in good condition and they should be closed. Okay, so containers, the plastic, the glass, the metal that you're storing this in, they should be, you know, I don't mean to say new, but they shouldn't be damaged in any way. No leaks, no holes, no corrosion, nothing like that. And they should stay closed. Hazardous waste should be stored safely prior to removal from the laboratory, and don't let it accumulate. What I mean is, don't collect waste for, you know, 5 or 6 years and then try to throw out like 50 gallons of it. You know, every semester, every second, third semester, like minimum once a year, we get someone to the college to dispose of the waste. Okay, usually sometimes every semester, sometimes once in the fall, and then once in the summer, we'll get someone to come and dispose of the waste. The containers obviously should be sturdy, so you can pick them up and move them, leak-proof, and have a label. Sturdy, leak-proof, label. All liquid waste are in leak-proof containers with screw top or secure lids. Snap lids, missized lids, this is wax lids, and loose fitting lids, not acceptable. They should be screw top or secure in some way. If necessary, the waste has to be moved to a container that can be closed. And again, like I just mentioned, we always keep them closed. The only time you would open a waste container is when you add more waste. And then the last thing, typically some of our wastes, liquid waste especially, we have a secondary containment that should be in place to capture any spills or leaks from the primary container. So what I mean is, you might have a bottle, right? You got your screw top on the bottle, you got your bottle labeled. You might have a few bottles, right? So different bottles with different waste, but then we would put these bottles in another container. So if something happens to this bottle and it leaks, it would go into a secondary container. So we might store these chemicals in the fume hood, or we might store them in the fume hood in a smaller container to protect against leaks. The one example I can give you about our lab is in the storage room. Acids and bases are stored in separate cabinets, keeping them away from anything flammable or oxidizing. It'd be nice if we were in the college right now, because I could take you to the chemical storage room and where we put our waste and just kind of show you. I look after waste, of course, but we have someone special on staff, like a specialist who looks at it, more particularly than us. And her name is, it's not Susan anymore. Delia, Delia, Delia. It was Susan. Now we have Delia. We took her from the engineering faculty this semester, or fall semester, and she would help us and look at most of the waste disposal at the college. So it would have been nice for you guys to talk to her, but anyways, that's it. So guys, I'm done for today. Thank you, Fatima, Heba, Nahala, Sophia, for sticking around this long class there, about an hour and 15 minutes, I think it was. That's it for the whole course. You guys, you have a bit of work to do for me. You have another lab. The lab, guys, is very quick. If you haven't done the lab yet, don't worry about it. The video is 8 minutes, and the write-up is I wouldn't say even quicker, but very quick. So I know you guys got a lot of work to do, but try to get those quizzes done before Thursday midnight, or Thursday at 11 p.m. And I will have your marks online either later that night. I'm going to stay up a bit late and get your marks in, or Friday morning at the latest. So when all of your marks are in, you can look at your quizzes. You can look at any questions you want to review for the final exam. Now, the last thing I'll mention, and then you guys are free to go. The final exam is obviously online. I will post some more information about this today on the D2L news feed. But the way that it will work is it will basically be like your quizzes you've been doing all semester, just a lot longer. Okay, it's worth, I think, 20% of the course. You can see that in the course information sheet. So it's worth a fair amount. It's basically like a really long quiz. It will have multiple choice, true and false, fill in the blank, and matching. Again, exactly like your quizzes you've been doing with me all semester. So your final exam, and it will have a few like short answer. So keep that in mind. You want to keep your notes open. I might ask you to explain very briefly a couple of things. So your final will include some multiple choice. Wow, sorry guys, my pen. All right, my pen just decided to die at the worst possible time. I'm sorry guys. Hold on, let me just move the battery. I'll get a new battery today. I think I'm gonna run out. I gotta get some stuff. Yeah, okay, guys. Oh, there we go. So your final would include multiple choice, true and false, matching. It would also have some fill in the blanks. and then short answer. Okay, you guys will have time to do this. You'll have a few hours to do this. It will be open on Saturday at 8 a.m. and it will close later that afternoon. And I'll post all of this on the D2L, and I'll post, specific times. I'll have a better idea, guys, about the number of these questions when I finish your quiz today or tomorrow. I'm working on the final exam as we speak. I'm reusing some questions from some of your old quiz. I'm using new questions, but nothing hard or nothing that I haven't covered in class. And you will have, a couple multiple choice, true and false and matching, a few fill in the blanks, and a few short answers. And I'll let you know more about the numbers as I finish that quiz. Tomorrow, this would be Wednesday at 1:30 p.m. I will be on Zoom if you have any questions. Sorry, guys, about the pen. So tomorrow, Wednesday at 1:30 p.m., I will be on Zoom if you have any questions. This is optional. You do not need to be there, but you are more than welcome to come in and ask questions. I will also be around Thursday if you have any questions. Now, I won't have a set Zoom time like at 1:30, but if you guys want to talk to me tomorrow, Thursday, Friday, or anytime on Saturday, you can send me an email. All right? So guys, that's it for the course. Thank you. I have your attendance and everything done. I'm going to hit stop record. So thank you very much. I know this has been a weird semester and a little boring at times online, but thank you again for that. So I'm going to hit stop recording. And if there's any questions, you can let me know. All right. Thanks again. Bye-bye.